Today I'm going to talk about the analytic methods to finding limits. There are 3 of them. So using 3 analytic methods to find limits. These methods are going to be used when you get a 0 over 0 after direct substitution. So use these methods only when direct substitution yields a 0 over 0. Right? If you're not getting a 0 over 0, then direct substitution is all that's necessary. Let me try to focus this better. Okay. So the first analytic method is just called the factor and cancel method. That's when you have a fraction that has factorable numerator or denominator. Just simplify a rational expression. And you've done that a lot since probably Algebra 1. Just simplify a rational expression, which is just a fraction. Okay. So for example, if you are trying to find the limit as x approaches -3 of x squared plus x minus 6 all over x plus 3. Well, direct substitution, if you put a -3 into this, you would get 9 minus 3 minus 6. So that would be a 0 in the numerator, and -3 plus 3 in the denominator would give you a 0 too. So right here, direct substitution of x equals -3 yields a 0 over 0. Right? If this were our function, if I called this f of x, and I said, what is f of -3? Well, f of -3 would be 0 over 0, or an indeterminate form. So we're going to use the method called factor and cancel, because what we have is a numerator that can be factored. So we're going to find the limit as x approaches -3 of x plus 3 times x minus 2 all over x plus 3. The x plus 3's cancel, so we are finding the limit as x approaches -3 of x minus 2. So all we have to do now is use direct substitution. So the limit as x approaches -3 of x minus 2 is equal to -3 minus 2, which is equal to -5. If you put this function in your graphing calculator and you looked at the numeric method, if you looked at the table of values as x is getting close to -3, like if you looked at -2.99999 or -3.00001, you would see those y values getting closer and closer and closer to -5. If you looked at the graph of this function, because our graphing calculators don't show the holes in the graph, there would be a hole at x equals -3. It would look like a straight line, x equals -2. The graphing calculator would show just that straight line. It wouldn't really show the hole unless you zoomed in so close that you could see it. But there really is a hole at x equals -3. But it would look like it would go through the y value of -5. So this is the analytic method to finding this particular limit, even though you could do it numerically on the table of values, or you could use the graphic method with a graphing calculator. It just depends on how I ask you to find this limit. This is the analytic method, one of them. Here's the second analytic method. Sometimes you're going to get complex fractions that you have to simplify. So for example, let's say you were trying to find the limit as x approaches 0 of 1 over x plus 1 minus 1 all over x. Well, what happens when you do direct substitution? If we put in x equals 0, we would get 1 over 0 plus 1. You get 1 over 1, which is 1, and 1 minus 1 is 0. So we would get 0 in the numerator and 0 in the denominator. So in this case, direct substitution yields a 0 over 0, which is an indeterminate form. Well, this isn't a fraction that you can do factoring and canceling like the previous example, but this is a complex fraction. So to simplify this complex fraction, we just find the LCD of all the three terms. Well, the LCD is x plus 1. So what you have to do is multiply each term by x plus 1. So we'll multiply this by x plus 1, we'll multiply this by x plus 1, we'll multiply this by x plus 1. So all three terms, and the reason we do that is to get rid of that fraction down there. So we're finding we keep having to write the limit as x approaches 0. This cancels, so you're going to get a 1 in the numerator minus 1 times x plus 1. Put it in parentheses because it's a subtraction, all over. Now we have x times x plus 1, which is x squared plus x. Now what we can do is simplify this fraction a little bit. So we have the limit as x approaches 0 of 1 minus x minus 1 all over. I guess I probably should have just kept this as x times x plus 1, not distributed back there. Now we can simplify this a little bit more because 1 minus 1 is 0. So we're left with a negative x on the top and a negative x over x. They can cancel out. So we actually are left with negative 1 on the top. So this negative x over this positive x cancels out to negative 1. So what we're left with is the limit as x approaches 0 of negative 1 all over x plus 1. And now we can do direct substitution. Direct substitution says I'm going to plug in a 0 for that x. So we get this equal to negative 1 over 0 plus 1, which is 1, which is negative 1. So that is the answer, negative 1. You just had to simplify that complex fraction down a little bit and then do direct substitution. There's a third analytic method, a third type of fraction that you're going to see. And this is when you have radicals in your fraction. You are going to do something called rationalize. And last year we rationalized denominators, or Algebra 1, I think you rationalized denominators, but that's not what we're going to do this year. We are going to do rationalize the numerator this year. What we have, or what we'll see several times in this course, is we're going to see something like this. The limit as x approaches something like negative 3 of this fraction, the square root of x minus 7 minus 2 all over x plus 3. So that fraction would look okay if we were back in Algebra 2, because in Algebra 2 we said, oh, you can't have a radical in the denominator, it's improper. Well, this year we're not going to keep this radical in the numerator, because if we plug in negative 3, oh, I'm sorry, this should say x plus 7 underneath here. If we plug in negative 3, we get negative 3 plus 7, which is 4, and the square root of 4 is 2, and 2 minus 2 is 0. So we get 0 over 0 after direct substitution. So just always make sure that direct substitution will yield a 0 over 0. Okay, so to rationalize the numerator, you're going to multiply the top and bottom, just like when you rationalized the denominator last year. To rationalize the numerator, multiply the top and bottom by the conjugate of the numerator. Okay, the conjugate of the numerator in this example is the square root of x plus 7 plus 2. So we're taking the limit as x approaches negative 3 of, I'm going to write the original one down, square root of x plus 7 minus 2 all over x plus 3, but we're going to multiply that by the conjugate of the numerator, x plus 7 plus 2 all over the square root of x plus 7 plus 2. And if you remember, when you multiply two conjugates together, all you have to do is multiply the first times the first and the last times the last. So what this would give us, the limit as x approaches negative 3 of the square root of x plus 7 times the square root of x plus 7 is just x plus 7. Negative 2 times positive 2 is negative 4. Because if you do FOIL, the O and the I will cancel out, so you don't have to do the whole thing. Now in the denominator, this becomes kind of tricky. Just make sure this x plus 3, this denominator here, goes in its own set of parentheses. And then the conjugate of the numerator goes in its own set of parentheses. It is the square root of x plus 7 plus 2. So you're just multiplying those two denominator parts together. Just put them in their own set of parentheses. So what happens in the numerator, and this is going to happen most every time, or it'll happen every time, if you simplify this down, x plus 7 minus 4, well, the plus 7 and minus 4 go to 3, so you're left with an x plus 3 in the numerator. And that x plus 3 and that x plus 3 are going to cancel out, so you're left with a 1 in the numerator. So what we have now is the limit as x approaches negative 3 of 1 over the square root of x plus 7 plus 2. And now when you do direct substitution, you're going to get 1 over the square root of 4, which is 2, plus 2. So direct substitution now gives you 1 over the square root of 4 plus 2, which is 1 over 2 plus 2, which is 1/4. So that would be your limit for this one. Now just be careful. Oh, if I can write, be careful on something like this. What if you have the limit as x approaches 1 of 4 minus the square root of x all over x minus 16? After we do enough of these types of problems, a lot of times people see a fraction that has a radical in the numerator like this, and immediately they say, oh, I'm going to have to rationalize the numerator because I have a radical up there, and this fraction or this example is just like this example that I just did up here, so I'm going to go through all that work to rationalize the numerator. But direct substitution is what you should have done first, because direct substitution would give you 4 minus the square root of 1 all over 1 minus 16. 4 minus 1 is 3. 1 minus 16 is negative 15, and that would just give you a negative 1/5 for the answer. So this limit of this function as x approaches 1 is just really f of 1, which is negative 1/5. You don't have to use the rationalization technique unless you have a 0 over 0. And I'd like to wrap up this lecture today with talking about 3 conditions which under which the limits fail to exist. So far what we've looked at in these examples are limits that do exist because we can reach a certain number. So let's talk about 3 conditions for which they don't exist. Three conditions where limits fail to exist. The first condition is the function approaches a different number from the right than from the left. And we've looked at those in the past. The function approaches a different value from the right and left. For example, if we are trying to find the limit as x approaches 0 of the absolute value of x all over x. Well, this limit, if you do direct substitution, you would get a 0 over 0. Well, there's no analytical technique that we've just learned. We can't factor this. This is not a complex fraction, and this is not a rationalize the numerator case. So we would look at this either numerically or graphically. So let's look at this graphically. Take our graphing calculators out and get the absolute value of x all over x. And I think I've shrunken my window down. Yeah, I'm going from -3 to 3, and my y's are -3 to 3. So I'm kind of zoomed in here. And if I look at this graph, and if I look at the y value as x approaches 0 from the left, this y value equals -1. If I'm approaching x equals 0 from the right, this value is equal to +1. So what happens is we have two different values from the left and from the right. Graphically, this would look like this. And there's actually an open circle here because when x equals 0, this function has no value. It's undefined. So this is the graph of the absolute value of x over x. And from the left, the function, the limit as x approaches 0 from the left-hand side, which is that little minus of the absolute value of x over x, is equal to -1. All right, here's the -1 value. But the limit as x approaches 0 from the right-hand side of the absolute value of x over x is equal to +1. You're getting close to 0 from the right-hand side, and that value is +1. And I think I said this in the last video, that if these two are not equal to each other, then there is no limit. So that is one condition where the limit fails to exist. It approaches a different value from the right-hand side and from the left-hand side. The second condition where a limit would fail to exist is the function increases or decreases without bound. It's actually going to infinity. Increases or decreases. It's called without bound. And what that really means is the graph goes to infinity or negative infinity. So for example, if you're trying to find the limit as x approaches 0 of 1 over x squared, or it could be 1 over x, it really doesn't matter. Okay, if you use direct substitution, you would get you'd get 1 over 0, which is undefined. And there's no analytical technique to simplify this down. So what you would look at is the graph of this. That's the easiest way to find out if something goes to positive or negative infinity. So we have 1 divided by x squared. And if you look at this graph actually goes up forever and up forever from the left or from the right. So graphically, we would just put a little arrow on the end here. And as x is getting closer and closer and closer to x equals 0 from the left and from the right, they both go to infinity. And if you just put in y equals 1 over x instead of 1 over x squared, from the left it goes to negative infinity, from the right it goes to positive infinity. So there's another case where the limit fails to exist. This is increasing without bound, and in this case this decreases without bound. Decreasing means it's going down to negative infinity. So there's the second case where a limit would fail to exist. And the third case, and this is with trig graphs, the function oscillates. Oscillate, I think I mentioned this in class, it goes up and down and up and down and up and down. O-S-C-I-L-L-A-T-E-S, oscillates. It's like a spring going up and down and up and down. Graph jumps up and down. All right, this is like the limit as x approaches 0 of the sine of 1 over x. If we put this in our calculator, and let's clear this out, we'll get the sine of 1 over x. And if we look at this graph, oh, it's kind of fast, but if we zoomed in here, let me zoom in a little bit closer. Let me get my window to be from negative 0.5 to positive 0.5. I think we can see a little more oscillation going on here. So this graph is actually jumping up and down and up and down, and if we keep zooming in and zooming in, you can see more and more oscillation. If it jumps up and down, this graph actually goes from -1 to +1, -1, +1 if we keep on shrinking our windows down. So that is the third function, or the third reason why a limit would fail to exist. And I think that's about it for today.